Okay, hello everyone. I'm the team leader of Team Aerial, Hong Yusu, and let's take a look at a demonstration video.
This is Team Aerial's project report. Our experiment investigates the intermediate axis theorem and its interaction with fluid dynamics, aiming to explore potential applications in space systems. Experimental background. The intermediate axis theorem, or Janibekov effect, describes how a rigid body rotates unstably about its intermediate principal axis of inertia. This phenomenon was first observed in microgravity by Soviet cosmonaut Janibekov in 1985. The theorem traditionally assumes the body is rigid, meaning its internal structure remains fixed during motion. However, if the body contains fluid, its internal mass distribution changes dynamically during rotation. Our experiment introduces fluid into this system, focusing on how it affects rotational stability and the conditions predicted by the theorem. To test this concept, we designed T-shaped straws and divided them into 3 groups. 1. Control group, a hollow T-shaped straw representing a rigid body. 2. Experimental group 1, a straw half filled with water allowing partial fluid motion. 3. Experimental group 2, a straw fully filled with water approximating a rigid body with internal fluid. Each straw was rotated about its intermediate axis, axis 2, and we observed fluid redistribution, changes in the moment of inertia, I2, and rotational stability. Discussion of experimental groups. Experimental group 1, half-filled T-shaped straw. When the straw is half-filled, centrifugal force causes the water to redistribute toward the ends of the T-shape. This increases the moment of inertia, I2, stabilizing the rotation by delaying the instability predicted by Euler's equations. However, the water's delayed response to the straw's movement introduces complexity. Internal oscillations and minor instabilities may arise, depending on the rotation speed. This group highlights how fluid redistribution dynamically alters rotational behavior, allowing the system to adapt and achieve relative stability. Experimental group 2, fully filled T-shaped straw. When the straw is fully filled, the water and straw rotate cohesively, approximating a rigid body. Initially, the system follows the classic intermediate axis theorem. However, during rapid flips or changes in angular velocity, the fluid's viscosity and internal flow disrupt stability. These effects can lead to incomplete flips or irregular oscillations, demonstrating that even in a cohesive system, fluid dynamics play a critical role in rotational behavior. In experimental group 1, the increase in I2 caused by fluid redistribution prevents simple harmonic motion, stabilizing the rotation. In experimental group 2, the cohesive motion of the water approximates a rigid body but remains sensitive to viscosity and boundary effects, which disrupt stability under dynamic conditions. This experiment highlights the need for further investigation into how fluid dynamics interact with rotational systems under varying conditions. The findings suggest that understanding the interplay between internal fluid motion and rotational stability could lead to innovative approaches in designing spacecraft and satellites. Key questions remain, such as how to predict the effects of fluid redistribution in complex geometries, or how viscosity influences stability thresholds in microgravity environments. Addressing these questions through additional experimentation could pave the way for more reliable and efficient space systems.